According to the 2020 National Electrical Code, Section 250.50A3, a Ufer ground can be used where the grounding electrode is the metal frame of a concrete-filled metal raceway, embedded and concealed in or under a concrete foundation. Section 250.53A requires that additional grounding electrodes be installed if rods are used. The concern that an electrical contractor raised regarding the use of both rods and a Ufer ground is based on a misinterpretation of the National Electrical Code. The code does not prohibit the use of both rods and a Ufer ground. In fact, it specifically allows for the use of additional grounding electrodes, which would include Ufer grounds. The claim that grounding rods and a Ufer ground will communicate is incorrect. The Ufer ground is a solid copper conductor embedded in concrete, while the grounding rods are driven into the soil. These two systems are not connected and cannot create a dangerous situation. In fact, using both rods and a Ufer ground provides a redundant and enhanced grounding system that improves safety by reducing the likelihood of ground faults and electrical shocks. Therefore, both grounding rods and a Ufer ground should be installed to ensure a safe and code-compliant electrical system. A grounding electrode system is a crucial component of electrical safety, designed to provide a low impedance path for fault current to return to the source, thereby tripping a circuit breaker or fuse and preventing electrical shock hazards. It consists of one or more grounding electrodes bonded together to form a comprehensive network. Firstly, let's consider the components of a grounding electrode system. These typically include items like ground rods, ground plates, underground metallic water pipes, metal building frames, and concrete encased electrodes, commonly known as Ufer grounds. Each of these electrodes plays a role in dissipating fault current into the earth. Secondly, the purpose of a grounding electrode system is multifaceted. Its primary function is to provide a stable reference point for electrical systems, ensuring that all non-current carrying metal parts are at or near ground potential. This minimizes the risk of electric shock by preventing voltage differences between accessible metal surfaces and the earth. Thirdly, a low impedance path to ground is essential for effective fault current clearing. When a fault occurs, such as a short circuit between a hot conductor and a metal enclosure, the grounding electrode system provides a pathway for the fault current to flow back to the source. This high current flow triggers the overcurrent protection device, such as a circuit breaker, to trip and interrupt the circuit, preventing further damage and potential hazards. Fourthly, the National Electrical Code, or NEC, outlines specific requirements for grounding electrode systems to ensure safety and compliance. These requirements cover the types of electrodes that can be used, their installation methods, and the bonding connections between them. Adherence to these standards is crucial for creating a reliable and effective grounding system. Fifthly, the Ufer ground, also known as a concrete encased electrode, is a type of grounding electrode that consists of a steel reinforcing bar or bare copper conductor encased in concrete. It is typically installed in the foundation or footing of a building and provides excellent grounding due to the large surface area in contact with the earth. Sixthly, ground rods are another common type of grounding electrode. They are typically made of copper or copper-clad steel and are driven into the ground to provide a direct connection to earth. The number and spacing of ground rods are determined by factors such as soil resistivity and local code requirements. Seventhly, proper bonding and interconnection are essential for creating an effective grounding electrode system. All grounding electrodes must be bonded together using appropriate bonding conductors and connectors to ensure that they are at the same potential. This minimizes the risk of circulating currents and voltage differences that can create safety hazards. Eighthly, regular inspection and testing of grounding electrode systems are necessary to ensure their continued effectiveness. This includes visual inspections to check for corrosion or damage, as well as electrical testing to verify the integrity of the grounding connections and the overall impedance of the system. Ninthly, the benefits of a properly installed and maintained grounding electrode system are numerous. It provides enhanced electrical safety by reducing the risk of electric shock, protects electrical equipment from damage due to fault currents, and improves the overall reliability and performance of electrical systems. Tenthly, in conclusion, a grounding electrode system is a critical component of electrical safety. It plays a vital role in protecting people and property from electrical hazard. By understanding the principles of grounding and adhering to relevant codes and standards, we can create safer and more reliable electrical systems for our homes and businesses. Grounding electrode systems serve as a critical safety mechanism in electrical installations, designed to protect individuals and equipment from electrical hazards. The primary function of a grounding electrode system is to provide a low impedance path for fault current to return to the source, facilitating the rapid operation of overcurrent protection devices such as circuit breakers or fuses. Firstly, understanding the basic principles of grounding is essential. Grounding refers to the intentional connection of electrical systems and equipment to the earth, establishing a common reference point for voltage potentials. This connection helps to stabilize voltage levels and minimize the risk of electrical shock. Secondly, the components of a grounding electrode system typically include grounding electrodes, bonding conductors, and grounding electrode conductors. Grounding electrodes are conductive elements that make direct contact with the earth, while bonding conductors connect various metal parts of the electrical system to ensure equipotentiality. The grounding electrode conductor connects the grounding electrode to the electrical system's grounding bus or neutral point. Thirdly, there are several types of grounding electrodes commonly used in electrical installations. These include ground rods, ground plates, underground metallic water pipes, metal building frames, and concrete encased electrodes, often referred to as Ufer grounds. Each type of electrode has its own advantages and limitations depending on soil conditions, installation requirements, and local code regulations. Fourthly, ground rods are perhaps the most widely used type of grounding electrode. They consist of metal rods, typically made of copper or copper-clad steel, that are driven into the earth to provide a direct connection to ground. The depth and spacing of ground rods are determined by factors such as soil resistivity and local code requirements. Fifthly, ground plates are another option for grounding electrodes, particularly in areas where it is difficult to drive ground rods due to rocky soil or other obstructions. Ground plates are typically made of copper or other conductive materials and are buried horizontally in the earth. Sixthly, underground metallic water pipes can also be used as grounding electrodes, provided that certain conditions are met. The water pipe must be in direct contact with the earth for at least 10 feet and must be electrically continuous throughout its length. Additionally, the water pipe must be supplemented by another grounding electrode, such as a ground rod or ground plate. Seventhly, metal building frames can serve as grounding electrodes in certain situations, particularly in large commercial or industrial buildings. The metal frame must be effectively grounded and bonded to the electrical system to ensure proper grounding protection. Eighthly, concrete encased electrodes, or Ufer grounds, are becoming increasingly popular due to their superior grounding performance. A Ufer ground consists of a steel reinforcing bar or a bare copper conductor encased in concrete, typically in the building's foundation or footing. The large surface area of the concrete provides excellent contact with the earth, resulting in low grounding impedance. Ninthly, proper installation and bonding techniques are crucial for ensuring the effectiveness of a grounding electrode system. All grounding electrodes must be properly sized, installed, and bonded together to create a low impedance path for fault current. Bonding conductors must be securely connected to metal parts of the electrical system using approved connectors and methods. Tenthly, regular inspection and testing of grounding electrode systems are essential to verify their continued effectiveness. Visual inspection should be conducted to check for corrosion, damage, or loose connections. Ground resistance testing should be performed periodically to measure the impedance of the grounding system and ensure that it meets code requirements. 11thly, the National Electrical Code, or NEC, provides comprehensive guidelines for grounding electrode systems in Article 250. The NEC specifies the types of grounding electrodes that are permitted, the minimum size of grounding electrode conductors, and the bonding requirements for various metal parts of the electrical system. 12thly, the selection of grounding electrodes should be based on factors such as soil conditions, local code requirements, and the specific characteristics of the electrical system. Soil resistivity is a critical factor to consider as it affects the impedance of the grounding system. Low soil resistivity is desirable as it allows for better grounding performance. 13thly, the number of grounding electrodes required depends on the size and complexity of the electrical system. In general, it is recommended to install multiple grounding electrodes to provide redundancy and improve grounding effectiveness. The NEC requires a minimum of one grounding electrode, but additional electrodes may be necessary to meet code requirements or to achieve the desired grounding impedance. 14thly, the spacing between grounding electrodes is also important. Grounding electrodes should be spaced at least 6 feet apart to minimize the effects of overlapping zones of influence. Overlapping zones of influence can increase the overall impedance of the grounding system and reduce its effectiveness. 15thly, the use of exothermic welding, also known as CAD welding, is a common method for creating permanent and reliable connections between grounding electrodes and conductors. Exothermic welding involves using a chemical reaction to create a molten metal bond between the two conductors, resulting in a strong and corrosion-resistant connection. 16thly, grounding electrode systems should be designed and installed by qualified electrical professionals who have the knowledge and experience to ensure compliance with code requirements and best practices. Proper grounding is essential for electrical safety, and improper grounding can create serious hazards, including electric shock, fire, and equipment damage. 17thly, in addition to protecting against electrical shock, grounding electrode systems also play a role in protecting sensitive electronic equipment from damage due to voltage surges and transients. A properly grounded electrical system can help to divert surge currents away from sensitive equipment, reducing the risk of damage. 18thly, grounding electrode systems are not a substitute for other safety measures, such as ground fault circuit interrupters, or GFCIs, and arc fault circuit interrupters, or FCIs. GFCIs and FCIs provide additional layers of protection against electrical shock and fire hazards and should be used in conjunction with a properly grounded electrical system. 19thly, grounding electrode systems should be regularly inspected and maintained to ensure their continued effectiveness. Periodic inspections should include visual checks for corrosion, damage, or loose connections, as well as ground resistance testing to verify the impedance of the grounding system. 20thly, in summary, grounding electrode systems are a critical component of electrical safety, providing a low impedance path for fault current to return to the source and protecting individuals and equipment from electrical hazards. Proper design, installation, and maintenance of grounding electrode systems are essential for ensuring electrical safety and compliance with code requirements.